today's lecture we will start with isomorphism of graphs. Now, we have already seen that a graph G is an ordered pair of sets V and E, where V is called the set of vertices and E the set of edges. Now, we have also seen what we mean by vertices and edges. Roughly speaking, V contains some points and E contains pair of those points, not necessarily all the pairs, and each pair corresponds to an edge, and it may so happen that there may be repetition of these pairs, so that within two vertices there may be more than one edge, edges, as well as there may be self loops. Now, sometimes what happens is that we draw two graphs, but there may be a one-to-one onto mapping from the set of vertices of one graph to the set of vertices of the other, such that the adjacency of the vertices are maintained, and in those cases we say that the two graphs are isomorphic. Now, we go for the formal definition. It says that two graphs G and G dash are said to be isomorphic well, of course, to each other if there is a 1-to-1 correspondence between the set of vertices and the between the sets of vertices and the sets of edges so that the incidence relationship is preserved. Now, let us look at an example. Now, we have drawn two graphs. Let us call this graph G and this graph G prime. Now, apparently they are different graphs, but I will now give a one-to-one onto correspondence from the set of vertices of G to the set of vertices of G prime, and a one-to-one correspondence, one-to-one onto correspondence from the set of edges of G to the set of edges of G prime, and we can check that the incidence relationship is preserved, or in another way the adjacencies are preserved, that if two vertices are adjacent in G, they will become adjacent in G prime, and the corresponding edges also will be mapped to the corresponding edges. So, I will give the mapping. So, isomorphism of G to G prime. So, one side I write the one-to-one onto maps between the set of vertices, and the other side the one-to-one and onto maps between the set of edges. So, between the set of vertices we have A map to V1, B map to V2, C map to V3, D map to V4, and E map to V5, and among the set of edges 1 map to E1, 2 map to E2, 3 map to E3, 4 map to E4, and 5 map to E5. Now, let us look at the first few correspondences. So, A is mapped to V1. So, that means A is going over here, and B is mapped to V2. That means that B is going to this point. Now, A and B are adjacent to each other in the graph G. Now, let us look what happens in graph G prime. Here we see that V1 is adjacent to V2, and what about the edge which is connecting A and B? The corresponding edge is 5, and here we see the corresponding edge is E5, and according to our already defined correspondence, we see that 5 maps to E5. That means, according to this map, A is going to V1, B is going to V2, and AB, the edge AB that is labeled by 5 in the graph G, is getting mapped to the edge E5, and which is the edge between V1 and V2. And this should happen with each vertices, each vertex and each edge. If it happens, then we say that we have an isomorphism. It is needless to say that finding out isomorphisms between two graphs is a very difficult problem, and we do not have complete answer to this. So, that means that if I am given two graphs in general, I do not have a quick or efficient way of deciding in general whether these two graphs are isomorphic or not, but we can always hope to get some partial results depending on certain properties of the graphs. Now, let us look at some partial results. partial results on decision of isomorphism of graphs. Now, what we will do here is that we will list down 3 rules or 3 conditions that 2 isomorphic graphs must have. We will of course show later with an example that even if these conditions are satisfied, it does not mean that the graphs are isomorphic. What we can say is that if 2 graphs are not isomorphic, then what we can say that if these conditions are not satisfied by these any 2 graphs, then they cannot be isomorphic. I repeat again, we will give 3 conditions. Now, what we will claim and what is very evident is that if there are 2 graphs for which these conditions are not satisfied, then they cannot be isomorphic. However, we will give examples and show that there are graphs which satisfy these properties and still they are not isomorphic. Now, let us look at the properties. All right. So, if we have 2 isomorphic graphs, then they must have same number of vertices and they must have the same number of edges. Three, an equal number of vertices with a given degree. Now, it is not difficult to directly see that these conditions are absolutely necessary for 2 graphs to be isomorphic. That means that if 2 graphs are isomorphic, of course, these things must happen. So, if these things do not happen, then they are not isomorphic, but it is quite possible that these things do happen, but still the graphs are not isomorphic. Let me give an example. Now, we have a graph which we denote by G and another graph we denote by G prime. Now, G has 6 vertices, G prime also has 6 vertices. Now, if you look at the edges, G has 4 edges, G has 5 edges and G prime also has 5 edges. Now, if we look at the degrees, now there are vertices of degree 1, and in G there are 3 vertices of degree 1, in G prime there are 3 vertices of degree 1, and about degree 2 in G there are 2 vertices of degree 2, and in G prime there are 2 vertices of degree 2, and in G there is exactly one vertex with degree 1, exactly one vertex with degree 3, and in G prime there is exactly one vertex with degree 3. Now, what we claim is that these two graphs are not isomorphic. So, we have to show that they are not isomorphic, although it is now clear that if we look at these 3 conditions, G and G prime satisfy all these 3 conditions. Now, if we are trying to build an isomorphism, suppose we write G as V comma E and G prime as V prime comma E prime, we have to develop a one-to-one correspondence between V and V prime. Now, it is obvious that the vertices of the same degrees will be mapped to vertices of the same degree, because otherwise it is not possible to preserve the adjacency or incidence relationships. So, the vertex x, has to be mapped to the vertex y, because x is the only one vertex of degree 3 in V, and y is the only one vertex of degree 3 in V prime. Now, if we look at this region and this region, we see that from x, 2 vertices are connected which are of degree 1, but from y only one vertex is connected which is of degree 1. Therefore, there is a structural difference between these two graphs. If we think a little more, we will see that no matter how we arrange our permutations, or so to say the mapping between V and V dash, I will never be able to map all the vertices in such a way that the incidence relationship is preserved. That the reason is that, as I said, that there are 2 vertices of degree 1 getting connected to the degree 3 vertex, and here there is only one vertex of degree 1 getting connected to the degree 3 vertex. Therefore, G and G dash are not, G and G prime are not isomorphic. although they satisfy the three conditions given above. Although they satisfy the three conditions given above. Next, we move on to subgraphs. If we have a graph, let us denote it by G equal to V comma E, we can always think of a subset of V. Well, let us call it V prime, which is a subset of V, and we can consider a subset of E such that the endpoints of that subset, let us name it E prime, belongs to V prime, such that the endpoints slash end vertices of the elements in E prime are in V prime. Then the resulting graph, which is in some way a smaller graph than G getting derived from G, is called a subgraph of G. Let me write the definition more systematically. A graph G prime is said to be a subgraph of a graph G if all the edges of G prime are in G and each edge of G prime has the same end points or end vertices in G prime as in G. So, this is in a formal way of defining a subgraph, but we can always remember what I have told in the beginning, that a subgraph will have possibly a lesser number of vertices, and edges will pick up the edges from the set of edges of G which has got endpoints in that subset of vertices. Now, we have got some observations related to a subgraph. One, every graph is its own subgraph. Well, this is of course obvious. Then 2, a subgraph of a subgraph of a graph G is a subgraph of G. This 2 is something that goes without saying. And third, a single vertex in a graph G is a subgraph of G. That is also direct from the definition. And 4, a single edge in G together with its endpoints is also a subgraph of G. We see that these are more or less straightforward. Now, we will move on to certain special types of subgraphs which are important in several applications of graph theory. Now, we come to edge disjoint subgraphs. Edge disjoint subgraphs. Two or more subgraphs G1, G2 of a graph G are said to be edge disjoint if G1 and G2 have no edge in common. Now, let us look at an example. Suppose we have a graph like this. So, let us label the vertices V1, V2, V3, V4 and V5 and label the edges E1, E2, E3, E4, E5 and E6. So, let us call this graph as G. Now, let us look at a subgraph of this type. V3, E4, no, it is not E4 over here. So, V3, this is the vertex V3, E3 is over here, E1 is over here. V1, E2 and V2, and another subgraph V3, V4, here this is V5. So, this is V5 like this, and we have E4, E5 and E6. Now, suppose I write G1 as V1, V2, V3 and E1, E3, E2 and G2 as V3, V4, V5 and E4, E5 and E6. Then G1 and G2 are edge disjoint subgraphs. See that this is the set of edges for G1 and this is the set of edges for G2, and there is no common edge, but it does not mean that they do not have common vertices. We see that the vertex V3 appears in both the sets of vertices of the subgraphs. Now, we come to vertex disjoint subgraphs. Two edge disjoint subgraphs are said to be vertex disjoint if they do not have any common vertex. Now, let us look at an example of a subgraph of a graph. Let us consider this graph where the vertices are labeled by 1, 2, 3, 4, 5, 6 and the edges are labeled as A, B, C, D, E, F, G. Now, let us consider another graph. Now, this is of course a subgraph of the original graph. So, let us name it G and let us name it G prime. G prime is clearly a subgraph of G. Before I end today's lecture, I will introduce few more terminologies. One is an isolated vertex. A vertex of degree 0 is said to be an isolated vertex. Then a pendant vertex a pendant vertex and a null graph. A graph with no edge is said to be a null graph. Now, for isolated vertex, an example may be like this. Suppose I have a graph over here, a vertex like this. So, suppose this is V 1, V 2, V 3, V 4 and a vertex is over here which is called, let us say, V 5. This V 5 is will called an isolated vertex. And a pendant vertex will be a vertex which has got only one degree. So, possibly like this V 1, V 2, V 3, V 4 and V 5. This is a pendant vertex, and a null graph will be graphs of this type which has got only vertices, but the set of edges is a null set. And then there is an idea of regular graphs. A graph in which each vertex has same degree is called a regular graph. And if this degree is, let us say, d, then it will be called a d-regular graph. Now, we think of again the isomorphism problem. Here we will see that it is very difficult to solve the isomorphism problem for two d regular graphs, whatever be the value of d, which has the same number of vertices and the same number of edges. With this, I end today's talk. Thank you.